by exerting an equivalent opposite force, that is F is equal to plus kx. This object is displaced a small distance dx without acceleration, therefore force remains constant. Now for this small displacement, we can write the formula dw is equal to f dx or f dot dx. This is the actual way. So dw is equal to f dx cos theta. Here theta 0, theta 0, theta 0, and cos 0 is equal to 1. Therefore, dw is equal to f dx. Now, total work done in stretching it from 0 to x. 0 to x is f dx. Then w is equal to 0 to x. Here f is equal to kx. Kx dx. W is equal to k into integral 0 to x x dx. Then w is equal to k into, this is integration. Integration x dx is equal to x to the power n plus 1 divided by n plus 1. So here power 1. Integration x to the power 1 dx means x squared by 2. So we can write here k, this will be after integration, that will be x squared by 2. And we have to apply the limit for x. X can have two values, initial value 0, final value x. Before applying the limit, we have to take that half outside, half k. Now x, initial value x and final value 0. Then we get w.
So should we write
half k x squared. This work is stored as elastic potential energy. This work is developed as elastic potential energy within the spring. Within the spring.
Sir,
then
please check your fitting room, sir.
EP is equal to, what is that?
Sir,
Diagram?
yes sir, drawn sir.
Sir,
Sir, this work is developed on relation.
What?
This work is developed
As elastic potential energy within the spring. So you have to write introduction, right? Write down. Let us consider a spring. Let us consider a spring of spring constant K. Let us consider a spring of spring constant K is stretched such that the extension produced is X. Is stretched such that the extension produced is X. The extension produced is X. Next line. Then restoring force developed within the spring. The restoring force developed within the spring is F is equal to minus Kx. Negative sign indicate restoring forces opposite to the extension. Opposite to the extension.
Sir, the restoring force within the spring.
F is equal to minus Kx. Here minus sign indicates restoring force is opposite to the extension. Now next line. By exerting an equivalent opposite force by an external agent. By exerting an equivalent opposite force by an external agent. By exerting an equivalent opposite force by an external agent.
Yes, someone is in the waiting room.
An external agent.
Someone is in the waiting room.
Nobody is there. Exerting an equivalent opposite force by an external agent, that is F is equal to plus Kx. Hasil 45. That is F is equal to plus Kx. The spring can be stretched a small displacement dx. The spring can be stretched through a small distance dx without acceleration. Without acceleration. Then work
But the
done
spring
for
can stretch. So can you repeat? The spring can stretch.
stretched through a small displacement dx without acceleration, because forces are equal and opposite. Without acceleration. Then work done for this small displacement. Work done for this small displacement is dw is equal to f dx. F dot dx. Actually, f dot dx. dw is equal to f dot dx. Then continue. dw is equal to f dx cos theta. F dot dx means f dx cos theta. Then theta 0 cos 0 1. dw is equal to f dx. Have you finished up to here? Then right. Total work done in stretching the spring. Total work done in stretching the spring.
Just a second, sir. Yes, sir.
Total work done in stretching the spring. Total work done in stretching the spring from 0 to x. From 0 to x. Total work done in stretching the spring from 0 to x. Now capital, right? W. W is equal to integral 0 to x f dx. Then completely fill it.
Then we have to complete till where, sir?
Sir, this is graphical method.
Second one, alternative method. Make an alternative method only if they ask you, right? Otherwise, don't write it. Okay. This is now dx.
Sir, this is for spring only, yeah?
Sir, what is
Spring,
the last
same
sentence?
Spring, same spring, another method. Your
What is the
extension.
last sentence?
Last sentence. This work is developed as elastic potential energy within the spring. Then W, we are writing EP, potential energy. This is extension. This is force, applied force. Applied force. When this is X, this is Kx. This is just F, we are writing F. Okay.
Sir, what is on the y-axis?
Applied force. Applied force. APPLIED. Applied force. So when you made an extension of X, Kx is the restoring force. So from the graph, area under the graph, W is equal to area under the force extension graph. That is W is equal to half into area under OAB. Okay, graph OAB, half into length kx width x. So half kx squared. This way also work done can be calculated. So integration method and graphical method both are similar. Try to understand that. Is it over?
Yes, sir.
Next, kinetic energy. Kinetic energy. I told you when we do a work, if the object gain a speed, it is kinetic energy. Okay, right now. It is the energy possessed. Kinetic energy is the energy possessed by a body by the virtue of its motion. Kinetic energy is the energy possessed by a body by the virtue of its motion. In case if you don't get the word virtue, you can just write when it is in motion. That's all. Then expression for kinetic energy of an oscillating spring.
So what was that sentence? It is the energy possessed by a body by the virtue
of its motion. Expression for kinetic energy of oscillating spring. Oscillating spring. Expression for kinetic energy of oscillating spring. Suppose this is spring at A, position A. Where now this spring I am stretching to maximum distance B, that we can mark. This is 0, x is equal to 0. This point x is equal to x naught. And I'm releasing this spring. When it is this spring releasing, it will keep moving back. Okay. Will it stop at A again? The spring?
No, sir.
No, sir.
No. It will overshoot to the left side of that line, isn't it? So now, and it will compress. How much it expanded, you can see same distance it will get compressed. It will get compressed like this spring. Okay. So that will come to x naught, same way here. This is x is equal to x naught. X is equal to x naught. So here, what is the energy of the spring? EP? 0, right? Because
0.
half kx squared. X is 0 here. Agreed?
Yes, sir.
EP is equal to half kx squared. Just now we derived, isn't it?
Yes, sir.
When x is equal to 0, no energy stored in the spring now. Isn't it?
Yes, sir.
So here potential energy is 0. What is the potential energy at B in this situation?
Half k x
Half k square.
Half k
half
x
naught
naught
square.
squared. Maximum value, right?
Yes, sir.
Yes, sir.
Here also this is EP dash, half k x naught squared. But during its oscillation, potential energy will change from half k x naught squared to 0. Again half k x squared, x naught squared to 0, like that keep varying. Let us imagine a point in between when it is at a distance x. An arbitrary point. Suppose this is 10 centimeter. This is 0. This is minus 10 centimeter. At 5 centimeter or 6 centimeter or 7 centimeter, anywhere, that we can call just x. Okay, here what is the kinetic energy at distance x?
Half k x square.
Yeah, that is EP is equal to half k x squared, isn't it?
Yes, sir.
Draw the diagram. Now, right, let us consider a spring. Let us consider a spring oscillating on a frictionless surface. Oscillating on a frictionless surface. Oscillating on a frictionless surface. Let us consider a spring oscillating on a frictionless surface within the limits B and C. Within the limits B and C. With respect to mean position A. With respect to mean position A. The potential energy of the spring, when it has maximum displacement x naught, can be written as, instead of EP dash, better write E naught. Then easily we can remember E naught. Okay.
Sir, when it has maximum.
Mark it E naught. Let us consider the potential of the spring when it has a maximum displacement x naught. Maximum displacement x naught. The maximum value of potential energy. The maximum value of potential energy can be written as E naught is equal to see this value, half k x naught squared. This also mark E naught. E naught. Okay, half k x naught squared. Then by law of conservation of energy, here energy is not lost. In this case, when spring is moving, potential energy is converting into kinetic energy, and at the mean position, it will have complete kinetic energy. Then again, potential energy will increase to left side. And at the extreme position, it will have only potential energy. For example, this end, it has a potential energy of 10 joule. While it is moving, potential energy will become 9, 8, 7, 6, 5, 4, 3, 2. Here it is 0. And here again 1, 2, 3, 4. Here it will be 10. Now kinetic energy here 0, but here 1, here 2, here 3, here 4, 5, like that. Then this will be kinetic energy completely. Do you understand that?
Yes. Yes, sir.
This is happening in a conservative field. So the total energy remains same. In a conservative field, energy is not lost. Okay, write down. Then by law of conservation of energy, gain in kinetic energy have you written this step? Check during the oscillation of the spring at an instant when it is at x, potential energy is half k x squared. Have you written?
No,
Yes,
sir.
We wrote a potential energy when maximum displacement x0 is equal
E naught
to
is equal to half k x naught squared. Up to there you have
yes.
Yes.
So
Yes,
I'm
sir.
repeating once again, you check. Okay, once again from the beginning. Let us consider a spring oscillating on a frictionless surface within the limits B and C with respect to mean position A. Then potential energy of the spring when it is stretched to a maximum displacement x naught is E naught is equal to half k x naught squared. We have finished up to there.
Yes, sir.
Yes, sir.
Next line. During its oscillation, during the oscillation of the spring, during the oscillation of the spring, during the oscillation of the spring, at an instant, during the oscillation of the spring, at an instant, during the oscillation of the spring at an instant, when it is at a distance x, when it is at a distance x, potential energy EP is equal to half kx squared. Potential energy EP is equal to half kx squared. Then by law of conservation of energy, then by law of conservation of energy, then by law of conservation of energy, gain in kinetic energy is equal to loss in potential energy. Gain in kinetic energy is equal to loss in potential energy. That means gain in kinetic energy is Ek. Loss in potential energy at maximum value, it has a half x naught squared. Now it has half x squared.
So can you repeat
Year
last
to year. Gain in kinetic energy is equal to loss in potential energy. Gain in kinetic energy Ek. Ek, kinetic energy symbol. Maximum distance half k naught squared, here half kx squared. Then Ek is equal to half k x naught squared minus x squared. This is a formula. Then total energy in the spring, total energy is Et is equal to Ep plus Ek, kinetic energy plus potential energy. Ep is half k x squared plus Ek is half k x naught squared minus x squared.
Sir, what is ET?
Et, total energy.
Yes, sir.
Then here we can write Et, total energy is equal to half k x squared plus half k x naught squared minus half k x squared. This to cancel. Et is equal to half k x naught squared. That's the answer. Total energy.
graphical formula?
This is the reference line, okay? This I'm marking a dotted line.
Sir, alternative
The
method.
pink line.
This is a dotted line.
What is the pink line?
Pink line, actual axis, x-axis. So here 0, x is 0, here extension. This point x naught.
So this is
This
the
point,
alternative
x
method.
naught. Huh?
Alternative method.
No, it's a graph.
Graphical.
The following graph shows variation of potential energy, kinetic energy, total energy of a oscillating spring. This is energy. The following graph shows variation of which graph is this? If I am marking it, is it potential energy, kinetic energy, or total energy?
Kinetic energy.
All.
Kinetic energy. That means
Potential energy.
it's potential energy, because at the extreme end, potential energy maximum, kinetic energy is 0. Okay, so this is EP is equal to half k x naught squared. So this is potential energy curve. Okay, this one's going. Here also EP is equal to half k x naught squared. But here kinetic energy is 0. Kinetic energy here 0. But at this point, kinetic energy become half k x naught squared. But potential energy will be 0 here, because x is equal to 0 at this point. Here again, kinetic energy will be 0. So total energy is always half k naught squared. What is this graph representing? This line.
Kinetic energy.
What is this line representing?
Kinetic energy.
Kinetic energy. Yeah. So here we have marked kinetic energy 0 here, kinetic energy maximum. So this line, this violet line on the top, that represents total energy. Total energy. Total energy is a sum of kinetic energy plus potential energy. This is the graph.
So the blue line is kinetic energy.
Kinetic energy.
So where is the total energy?
On the top, see this upper one, this violet line.
So the orange line is potential energy.
Yeah. But examination, don't write orange line at all, okay? Examination, you should mark it in the diagram. See, this is the this black line is total energy. I think it's time, okay? So next class we'll start with kinetic energy of a moving body. Kinetic energy of a moving body will start in the next class.
Okay, sir. Thank you, sir.
Person who joined